Boring.
Now it's fine. Okay, so then Pedro, you can start.
Okay, so let me first share my screen. Um, okay, so let me put in full screen configuration, sorry. Um, oh, okay, so I hope you guys are seeing my screen and listening to me very well. So first, I would like to thank you very much, Leah, for inviting me to give the seminar. This is the first time I give a seminar to a research group outside Brazil, so it's a very new experience to me. Thank you very much. So as Leah said, my name is Pedro. I'm a PhD student in physics in the Federal University of Goiás here in Brazil. Okay. And Leah asked me to give this seminar and show my latest results regarding Krylov complexity and dynamical phase transition. So, so the results I'm going to show today, they are published here in this paper. It is a collaboration with Lucas Céleri, which is my PhD supervisor, and Adolfo Del Campo from the University of Luxembourg. Okay. All right, so I want to start this presentation speaking about Krylov complexity, okay? Maybe I'll spend most of my time speaking about Krylov complexity, since this is something new and we have seen a lot of papers coming out on arXiv every week, and so that's it. So the whole story behind the Krylov complexity started because of this very famous and a very studied problem nowadays, which is the thermalization in isolated quantum systems. Okay, so what I mean by thermalization in isolated quantum systems. So, for example, if you imagine that you have a quantum many-body system which is isolated, which means that this system is not in contact with a thermal bath or an environment in such a way that in your mathematical description, you're going to take into account only the internal degrees of freedom of your system, okay? And if you consider that this system is interacting and you choose a subsystem of the system, so for example, this subsystem A that I'm showing here, which contains only 4 sites of this 2D spin chain, for example, and if you wait an enough amount of time, so what you see is that after the subsystem B interacts with the rest of the system, which I call the subsystem B, then what you see is that the subsystem A is in a thermal state. Okay, so what it looks like is that the subsystem B acted like a thermal bath to the subsystem A, right? And you see this phenomenon in experiments for any subsystems A and B that you choose. Okay, so this is an open problem because we still don't know a general mechanism that explains this phenomenon and encompasses all the important details like many-body localizations, like the range of interactions, the differences that you can observe depending on the range of interactions and so on, which encompasses all the complicated details behind this phenomenon, okay? So the story behind the Krylov complexity starts because of this problem, okay? And for some reason, along the history of this problem of thermalization, the community decided to look at this problem in the Heisenberg picture instead of the Schrödinger picture. So they chose to see the operators evolve instead of the quantum states evolving as time passes. And because of that, we started to see this term in the literature, which is operator growth. Okay, so operator growth is no more than these operators which are evolving the Heisenberg picture. Okay, so so for example, imagine that you have a quantum many-body system which is isolated, and you choose an operator which is simple. That is an operator that in the beginning of the dynamics it is, for example, a local operator. Okay. So in the Heisenberg picture, the time evolution of this operator can be written in this way, okay? And then you can recast this expression in terms of this infinite series over here, okay? And here I wrote the first three terms of this expansion. So what we see when we expand the series is that it starts to appear these nested commutators between the Hamiltonian that you are using to evolve the operator and the operator that you chose to evolve, okay? So what these nested commutators do to this operator, well, you might have an idea. So for example, if you imagine that your isolated quantum system is a one-dimensional spin chain like this, and in the beginning of the dynamics, you chose an operator which has a non-trivial action only in one of the sides of this chain. Okay, so it is which means that this operator has an action which is different from the identity only in one side of this one-dimensional chain. So as you calculate the nested commutators, what you see is that the spatial support of this operator starts to spread through the system, okay? Which means that the non-trivial action of this operator starts to involve an increasing number of sides of the system, okay? So, when you do that time evolution that I wrote in the previous slides, there are more things happening to this operator in this system beyond the spatial support growth. Okay, so maybe the idea that the community, that the physicists that proposed this Krylov complexity idea is that besides the spatial support growth, you also this operator becomes more and more complex in a different way, which is the following. So we can imagine that this operator that you chose to evolve is an element of a different vector space, okay, which is not the usual Hilbert space of the quantum mechanics, whose elements are quantum states, but this is, instead of that, it is an operator Hilbert space. Okay, so now I have this new Hilbert space whose elements are operators, I mean matrices instead of quantum states, okay? And if you chose an operator to evolve, which in the beginning of the dynamics is a very simple operator, then you can imagine when t equals 0, this operator can be represented by a point in this new Hilbert space. And as time passes, it also starts to spread in this new operator Hilbert space, okay? And this is the idea that I'll try to explain in this seminar, okay? But okay, so all I have said so far is for the Heisenberg picture, but now I want to move to the Schrödinger picture, at least for two reasons. The first one is because it is easier to explain the idea, and the second one is because the results I'm going to show were calculated in the Schrödinger picture, okay? So please allow me to change to the Schrödinger picture now. And then instead of choosing an operator to evolve, you're going to prepare your isolated quantum many-body system, for example, in a specific quantum state psi 0. And because the system is isolated, the time evolution is given by this unitary operator, the exponential of minus I ht. H is the Hamiltonian. And then you can rewrite this expression in terms of this series. And now you have here acting on the initial state, the powers, instead of the Liouvillean, as I showed previously, which is the commutator of the Hamiltonian with the operator. Now I have powers of the Hamiltonian acting in this initial state, okay? And so in the Schrödinger picture, we can see what is going on here, looking, for example, at this heuristic figure that I drew here. So I have now the usual Hilbert space of the quantum mechanics, okay? And this point over here, it represents the initial state, and the time evolution can be seen generically as some kind of a trajectory in this Hilbert space, okay? And if I'm lucky enough, I could say that depending on the initial state that I chose to evolve and the Hamiltonian that I chose, for any time t, this trajectory can be restricted to a small region of this Hilbert space, okay, for any time t. So now I mentioned the problem that I would like to solve here, okay? So the question is how to find the minimal subspace of the Hilbert space, which contains the dynamics of this initial state for any time t, okay? So just a moment, okay. Sorry. So how to, let me come back just a little bit. So how to solve this problem? I mean, how to give an answer to this question, okay? So what I have to do is to look at this expression over here, because the action of the powers of the Hamiltonian on the initial state, it contains all the information. So it has complete information only about the portion of the Hilbert space visited by the system state psi t, okay? So what I would like to do is somehow perform some kind of orthonormalization of this set of quantum states and get as an answer now a set with a finite number of quantum states. And this set of states will work as a basis to this subspace of the Hilbert space, which contains the dynamics of psi 0 for any time t, okay? So if we are able to accomplish this task, then this set of states that I get as an output of this process is called Krylov basis, okay? And this Krylov basis is useful to expand states living inside that subsystem, which is called the Krylov subspace of the initial state psi 0, okay? But how to do this orthonormalization? I mean, this is not an easy task at first sight, because here in the left-hand side of this equation, I have an infinite number of states, right? Because the index n in that series that I showed you, it goes from 0 to infinity. And in the right-hand side of this expression, I have a finite set, a set with a finite number of quantum states. So how could I find these quantum states, okay? And what is surprising about this problem is that we know the answer to it at least since 1950, and the answer is the so-called Lanczos algorithm. The Lanczos algorithm does no more than a Grunsch-Schmidt orthogonalization, and it works like this. So the first state of the Krylov basis is the initial state itself, psi 0. The next one is obtained by applying the Hamiltonian on the first one, and afterwards normalizing it. So B1 is a normalizing constant of this state, okay? And the next states of the Krylov basis, they are calculated using this recursive method over here given by equation 4, okay? So it requires the previous two states in order to obtain the next one. And for each step of this method, you calculate the normalizing constant, Bn, and you also have this other constant here, An, which is given by this expression, okay? And you can ask me how, when does this recursive method stops? Well, it stops when you find a quantum state, which is represented as a vector matrix, right? So a column matrix, and all the elements in this vector are 0, okay? And because of that, you're gonna get a normalizing constant equal to 0 in this case. So we usually say when you find this normalizing constant equals to 0, the method stops. Okay. And what is the output of this algorithm? Well, you get these two sets of constants, which are called Lanczos coefficients. And you also get a set with a finite number of states, which is called the Krylov basis.
Pedro, so you will always stop that method, right? The worst scenario would be when you would reach the whole Hilbert space, but there will be a point when you converged. Okay.
Yes, that's right. Exactly
But
that.
you must use probably a cut 10 to minus 3, 10 to minus 6, something like that, not exactly 0.
Yes, yes, of course. You know, there are these numerical issues involved in the calculation because, of course, you have some computational error involved in each step of the calculation. But you can, okay, that's a good question. Usually what we do after we get a very small number, okay, at first, in the first moment, you get a very small number, then you say, okay, I think that the method stopped. Then you have to apply the method again because of these errors. So the Lanczos algorithm is very known for these numerical instabilities, okay? So the results that I'm going to show in the end of this presentation, I had to do this. So depending on the initial state that you chose and the Hamiltonian, you have to do this process again, and then you can be sure that the method stopped in that step, okay? All right, so let me continue. Okay, so what is interesting about this Krylov basis is that the generator of the dynamics, which in the Schrödinger picture is the Hamiltonian, it has a three-diagonal form in this basis. Okay, so if you take the Hamiltonian and you calculate in the Krylov basis, you get a matrix like this. Okay, the main diagonal here contains that set of constants A, and you only have non-zero terms only in the diagonal above and below the main diagonal. And the elements in these two other diagonals are the other Lanczos coefficients, which are the normalizing constants. Okay? All right, so this method based on the Krylov subspace, it's a method which goes much beyond just a method to finding these Krylov bases and so on, because it somehow helps you to understand what is going on in the dynamics. I mean, we could say that this is a method which practically maps any quantum problem into a one-dimensional problem. Okay, so let me show you how. So if we return to the Lanczos algorithm, that recursive method that I showed, so the states are calculated using this expression over here, right? What I did here is just I recasted the expression in a different way. So I moved some terms to the other side, and then you can rewrite the expression like this, okay? And after some manipulations, for example, after using the Schrödinger equation and applying the nth Krylov state as a bra by left, what you get is this differential equation over here, the equation 7, which involves the probability amplitudes of finding the system state in the nth Krylov state in the left-hand side of this equation. And you see that this differential equation, it tells me that the probability amplitude of finding the state of the system psi t in this state, it is linked to the probability of finding it in the next state of the Krylov basis and in the previous one. Okay. And because of this equation, maybe if you guys may have heard of this model called the tight binding model. Maybe you guys have some background on condensed matter physics, but if you don't have I can assure you that this differential equation is the same that you get in this tight binding model, okay? So this tight binding model is a model used in condensed matter physics, and it describes the behavior of electrons in a lattice, typically in isolated materials, in materials which are not metallic and so on. And then in these systems, the electron is tightly bounded to the atom where it belongs, to which it belongs. And this electron can only hop to the nearest neighbor side of this chain, okay? And because of this similarity between this differential equation and the same differential equation you get when you solve the tight binding model, we can see the dynamics in the Krylov subspace as using the same analogy, okay? So you can imagine a one-dimensional chain. Each side of this one-dimensional chain represents one of the Krylov states, okay? Because of that first step of the Lanczos algorithm, we know that when in the beginning of the dynamics, so when t equals 0, the system state is sharply localized in the first side of this chain. And as time passes, the wave packet, which represents this electron in this tight binding chain, it starts to move to left, and it starts to spread and delocalize in this chain, okay? And if you have already seen the tight binding model, so you can say that the hopping terms of the tight binding model here in this analogy is represented by the Lanczos coefficients B1. So B1, B2, and so on are related to the probability of this electron, or let's say this fictitious particle in this analogy, to jump to the nearest neighbor. And the terms A are related to the probability of being in a certain site and remaining in the same site, okay? But anyway, as time passes, psi of t delocalizes in the Krylov basis, okay? So in general, we could say that the dynamics in the Krylov subspace is equivalent to a hopping particle in a one-dimensional disordered chain, this tight binding chain that I just showed, okay? As time passes, psi t delocalizes in the Krylov basis, which in the analogy...
Pedro, may I ask, why disorder chain? I mean, disorder is not a needed ingredient here, right?
Yeah, the disorder here refers to the hopping terms, because these hopping terms, they can be very different from each other, okay? And it's in this sense, okay? You can have, for example, small hopping terms, and then suddenly this electron meets a very high probability or a very low probability to jump to the next site of the chain, and so on. So disorder is in this sense.
So disorder is like something like the method introduced to the system. I mean, if you see this as a tight binding model, those coefficients behave as random numbers, but this is something introduced by the method by itself, no?
Yeah, that's it.
Yeah,
That's
okay.
like that. Yeah.
Okay, thank you.
Thank you for the question. Okay. All right. So, for example, we know that if the Hamiltonian you are using to evolve your system is chaotic, then this delocalization process is going to happen exponentially fast, for example, okay? And then using this analogy with this fictitious particle hopping between the sides of that semi-infinite chain, which we call the Krylov chain in this context. So the average position of this particle shall reflect the delocalization, okay? So you see here in the equation 8, this is the average position of this particle, because the index n here, it says in which site this particle is, okay? So the index n here some kind encodes the position of this fictitious particle in this chain, okay? And this quantity over here was called Krylov complexity, okay? Because somehow this quantity shall reflect the complexity of the dynamics in this semi-infinite chain, okay? So I hope I have convinced you that when you use this Krylov subspace method, you are somehow mapping your quantum problem into a one-dimensional problem, okay? Because if you change psi 0 and if you change the Hamiltonian, what is going to change is only the B's and the A's, I mean the Lang's coefficient, okay? But you have exactly the same analogy, okay? Because we could say that the Krylov basis is the basis which three-diagonalizes the generator of the dynamic. Okay.
But
So summarize.
Pedro, sorry. Just,
Yes?
but you only keep. I mean, you only remain in a finite, let's say, regime. No, I mean with finite system size. If you consider this a one-dimensional problem, this one-dimensional system is always finite.
Yes, it is always finite. I mean, actually, you may be not too lucky, and you may have chosen an initial state and a Hamiltonian whose Krylov subspace coincides exactly with the whole Hilbert space, as Les said. Okay, so in this case, this semi-infinite chain is going to have an infinite number of sites because you are doing the calculation in the thermodynamic limit. But of course, if you are not making the calculations in the thermodynamic limit, this Krylov chain is always going to be finite, okay?
Okay.
Because let's say the trivial upper bound for the Krylov subspace, the dimension of the Krylov subspace space is always the dimension of the Hilbert space, okay? Okay, so summarizing what I have said so far, so the Krylov subspace is this minimal subspace in which the dynamics unfolds, okay? In principle, the Krylov subspace may be unique for each initial state. So that's why in the previous slides that I showed, I was denoting the Krylov subspace, specifying the initial state psi 0 in the notation, okay? Because if you change the state you are involving, the Krylov subspace, of course, it might change, okay? So this is unique for each initial state. And this is kind of obvious, let's say so, because we know that some states are more ergodic than others, okay? So some states can explore a bigger part of your Hilbert space than others, right? So the dynamics in the Krylov subspace can be as this process of delocalization in the semi-infinite chain, which we call in this context the Krylov chain, okay? And the hopping terms are given by the Lang's coefficients. And the average position of this fictitious part in this analogy reflects this delocalization, and this quantity is the so-called Krylov complexity, okay? All right. So this idea of Krylov complexity, it was firstly introduced in this paper over here. It was published in 2019 by Daniel Parker and his collaborators. So it has only 5 years and it has almost more than 500 citations, 300 citations or so. I mean, this is something that that is growing very fast in the literature. And we have seen this concept being applied in many areas. So we have seen papers using this concept for to study integrable systems, quasi-integrable systems, or chaotic systems, okay? This Krylov complexity has already showed itself able to distinguish topological phases of matter, okay? It has been used to probe equilibrium phase transition. It has been used to study open quantum systems. It has also been applied in quantum field theories, cosmology problems, and so on, okay? So this concept has spread very fast in the literature in these 5 years. Okay, so here it comes our motivation. Okay, so we asked ourselves, is this Krylov complexity able to say something about dynamical criticality in isolated quantum many-body systems? Okay, so how the Krylov complexity behaves when you have a critical phenomenon and which is happening in a non-equilibrium scenario. Okay, because this is something that we are very interested in. Lucas have been interested in the last years. Okay, so this is the question that we asked ourselves. Okay, and in order to make the explanation easier to me, let me already introduce the model that we used in our work in order to answer this question, which is the so-called Lipkin-Meshkov-Glick model. Okay, so Lea has many publications involving this model, so you guys may have seen these Hamiltonian before. The Lipkin-Meshkov-Glick model describes a system with n spins 1/2, which are connected. These spins are connected to each other. So we could say that this model is an infinite range interacting system. Okay. And these spins are coupled with the same coupling J. Okay. And you also have in this Hamiltonian this term over here, which describes a transverse magnetic field applied in these spins 1/2. Okay. And then you can recast the Hamiltonian in this form over here if you rewrite it using collective spin variables, as we say. Okay. And this picture over here is only to give, let's say, a visual, just to visualize how this system can be represented. Okay. So this is the Lipkin-Meshkov-Glick model. And what we have done in our work is we used a quenched protocol. So this is something that you guys may have already heard before. Okay, so here I show a graph. In the vertical axis, I show the magnetic field H, the magnetic field strength that I showed in that Hamiltonian. And the horizontal axis, I have time. Okay, so a quenched protocol works like this. So you have an instant of time t0 in which you perform a sudden change in this control parameter of your Hamiltonian, in this case, the strength of the magnetic field. Okay, and what we do is the following. So for any t less than t0, so this magnetic field has a specific value h0. Okay, and then you have a corresponding Hamiltonian for this value of h, which is h0. And then what we do is that, given this initial Hamiltonian, we prepare our system in the ground state of this initial Hamiltonian, okay? Specifically the LMG model. And then we do this sudden change in the magnetic field. And now if we change from H0 to HF, we have a new Hamiltonian, okay, for this new value of the magnetic field. And then we use this new Hamiltonian to evolve the initial state, which is the ground state of the pre-quenched Hamiltonian. Okay, so the language is the following. We have, we refer to H0 and HF as the pre-quench and post-quench control parameter, and H0 and HF, the Hamiltonians, as the pre-quench and the post-quench Hamiltonians of the dynamic. Okay. All right, so we use this protocol in our work, and in order to understand what this protocol can do to the LMG model, okay, so you might have heard that the LMG model, it allows a semi-classical description in the thermodynamic limit. Okay, so I can use the phase space to see what is happening in the system. Okay, so in this figure over here, in the first row, I show the classical phase space of the pre-quench Hamiltonian. Okay, so it has this structure over here. This point here is one of the ground states, because the ground state when h equals 0, okay, for some values of h, it is doubly degenerate. Okay, so the ground states correspond to this point and the symmetric one here. Okay, so it has a ground state with a positive magnetization in the z direction and a ground state with negative magnetization in the z direction. Okay, so let's say that I chose as the initial state this ground state over here with positive magnetization in the direction z. Okay, so if I perform a quench in the LMG model with a relative low intensity, so what we see is that in terms of the classical trajectories in the phase space, we see that the classical trajectory moves here in the same sector to which the initial state of the dynamics belongs. And this trajectory do not go too far away from the initial state. Okay. But here in the right-hand side of the figure, if I perform a quench in my system with a relative high intensity, so what we see is that this classical trajectory is now allowed to move through the entire phase space, okay? So it now can cross to the other side, okay? And between this regime and this other one, there is a specific value of the magnetic field, the control parameter of my system, in which if I perform this specific quench in my system, I see that the trajectory touches precisely this point over here, the origin of the graph, which corresponds to an unstable point in the phase space, okay? And for this specific quench, we see that the period of the classical trajectory goes to infinite, okay? And in terms of the magnetization as a function of time, what do we see? So for this first scenario, what we see is that the magnetization is going to oscillate around the value of the magnetization of the initial state, okay? And the amplitude of the oscillations is not too big, okay? But if you perform a high intensity quench in the system, what you see is that the magnetization oscillates symmetrically around 0, like this, okay? And for this specific value of quench that I just mentioned, what we see is that the magnetization in the z direction as a function of t, and here this magnetization is the total magnetization, okay? I'm summing the magnetization in the z direction of all the spins in my model. So what we see is that this magnetization exponentially decays as a function of time, okay? And the passage between this regime here in the left-hand side and this regime in the right-hand side, this change occurs abruptly in such a way that this phenomenon can be described in terms of a phase transition, okay? And how this phase transition is described? Well, instead of looking to the magnetization calculated in the ground state as we do for the equilibrium scenario, what we do is the following. We can take this long time average of the magnetization over here, okay? And of course, you can always normalize this constant using the system size. And what you get is this quantity over here, so the long time average of the magnetization. And when you see this quantity as a function of your control parameter, what you get is a Landau order parameter. That is a quantity which is finite for some values of the control parameter and abruptly changes to another value, in this case 0, for another interval of your control parameter, okay? And of course, if you calculate the derivative of this graph, you will see that here the derivative goes to minus infinite and then abruptly changes to 0, okay? So this is how this dynamical phase transition, let's say so, is characterized in this system, okay? And the point at which we see this abrupt change is the so-called dynamical critical point. So this number plays an equivalent role to the critical value of the magnetic field that we see in an equilibrium phase transition. And for the LMG model, the dynamical critical point is H0, which is the initial value of the control parameter that I chose, the pre-quench value, plus J, which is the coupling between the spins over 2. Okay. All right, so this is how this dynamical phase transition manifests itself. Okay. So just for the sake of comparison, I made the numerical calculation of the total magnetization in the Z direction using that Hamiltonian that I just showed for the LMG model. So here the blue curves show the behavior of the magnetization as a function of time for quenches before the dynamical critical point. Okay, so the quench line is lying in the left-hand side of that graph, sorry, in this region over here, okay? So the pre-quench value and the post-quench value both are lying in this interval. And the red curves, they refer to quenches which cross this dynamical critical point, okay? And what we see is that what I just mentioned in the first case, the magnetization oscillates around the magnetization of the initial state, okay? And for the quenches which cross the dynamical critical point, we see the magnetization oscillating symmetrically around 0. And if you calculate the area between the curve and the horizontal axis, so for the red curve, the negative part is going to cancel the positive part, and then you will get an integral equals to 0, which gives me this region over here. And for the blue curves, if you calculate the area between the curve and the horizontal axis, which is no more than the integral, then you get a finite value, which corresponds to this region over here, okay? So of course, if this region is positive or negative, it will depend on the initial state that you chose, because as I mentioned before, you have a twofold degenerate ground state, okay? One of them has negative magnetization and the other one has positive magnetization. So this graph that I show over here is for the case of the positive magnetization for the initial state. But if in this simulation over here, I chose the other one with negative magnetization. So what you see is that if you move in this graph over here from the right to left, when you get to this point, you see the curve going down and assuming a negative value, okay?
Pedro,
Yeah?
I have a question.
Okay.
Okay, so just when you refer at this initial condition, you
Okay.
start in your example, you start in this critical value of this double well, and I don't know if you analyze the initial condition when it's in the center, for example, in the critical one. I don't know what is the difference when you apply this method.
Okay. Yes, you can. So, for example, let me come back here. In my simulations, I always set J equals 1. Okay, it makes easier the calculations. And for example, if you choose H0 equals 0, then the dynamical critical point is 1/2. But if you choose H0, okay, so for example, if you choose H0 equals 0, then you have 1/2 as the dynamical critical point. And then I can, as you said, choose as the initial state, a state which lies exactly in the dynamical critical point, right? And what you see is that, well, it depends on HF. Each HF is lying in the right-hand side or in the left-hand side, okay? Because as in the equilibrium phase transition, what you have here behind this dynamical phase transition is a breaking or a restoration of a symmetry. In this case, it is an effective restoration or breaking of a symmetry in the state at a very high value of t, okay? So it depends on HF, but what you see is exactly what you should see in the thermodynamic limit is something like this. Okay.
Yeah, for example, here in this picture, well, essentially my question is the black dot is the critical, is the initial state that you select. And what happens if you start from the center, from the beginning? I think that the evolution is not, no, it's not possible. Well, it's an, I'm not sure, just is my
Yeah.
question.
I mean, you are referring to the magnetization as a function of time. I mean, the question is what you would expect in this case for the magnetization as a function of time. Is that your question?
Yes, because, well, in your previous slide, you show that the evolution, for example, when you select the critical value, essentially the center in the phase space is like an attractor, no? You see how these oscillations goes to zero, and my question is, okay, it is because you start so far maybe in the phase space around of the critical value where is the minimum, and my question is, okay, what happens if you start from the beginning in the state that is in the center?
Oh, okay. If I understood your question correctly, so if H0 or HF lies exactly in this point over here, which is the unstable point in the classical phase space, then what you see is something like this. So it doesn't matter if it is H0 or HF, okay? So I refer to the magnetization as a function of time. I hope I answered your question correctly.
But Pedro, I hope that sorry, I understood that you started from a doubly degenerate ground state of a Hamiltonian. So you can never start them from the origin, because this will not be ground state of any. So from the way you define your initial state, your initial it's very clear in this figure. So in your initial state, the black dot is always at the bottom of this doubly degenerate wells, or these identical wells. So in this respect,
yes, in relation with my question is just this point, because he from the beginning used the minimum one. And my question is, okay, if you start for other part in the phase space, what is the behavior of the initial or the trajectory in the classical sense?
I think I got it. So okay, so the literature behind the dynamical phase transition always say we always usually start the dynamics in the ground state.
Okay, I see.
Okay, so this is the usual prescription in order to find a dynamical phase transition. Okay, so this is a very good question.
I see.
Because you are saying that what happens if I start the dynamics in an excited state? Is that right?
Yeah, because your plot, remember me, something that is essentially like an attractor in the classical feature, and also in the open case is like the dissipation process, no? And I think that is so close to this idea. Okay, yeah, I gotcha.
Yes.
Thank you, Pedro.
Yeah. So just to finish, maybe I didn't do the calculations using as the initial state an excited state, because the prescription behind the dynamic phase transition is, as I said, choosing one of the ground states. Okay, but this is an interesting question that I still don't have an answer. Okay, so yeah, thank you for the question. All right, so okay, so this figure over here, it's almost this one. I mean, you see some kind of a similarity between this figure over here and the numerical simulations that I have done. Okay, so I just showed this graph over here only for the sake of comparison, because now I start to show in my result. Okay. All right, so the question is, how does the Krylov complexity behave in a quenched scenario in the LNG model? And the answer is it behaves exactly like the magnetization. So here I show the Krylov complexity normalized. So this lowercase j here is n over 2, where n is the number of sites in the LMG model. Okay. And again, the blue curves refers to quenches before the dynamical critical point, and the red curves refers to quenches which cross the dynamical critical point. Okay. And you see that they are almost the same graphs. The only difference is the scale in the vertical axis, because of course, complexity always must be a value equal or greater to 0. I mean, it would not make sense a negative value of complexity. But you know, the qualitative behavior of this result is exactly the same of the magnetization. Okay. So this is my first result. Somehow the Krylov complexity behaves as exactly as the magnetization. Okay. And in the end of this presentation, I'm going to justify this result. So we were able to make some analytical calculations, and we show how this is possible. Okay.
But one comment, Pedro, in
Yeah,
your previous slide, there is one temporal, the slide C, yes, it is, no, ACE, the top third, which has a different, it takes longer times to arrive to the equilibrium process. Can you comment about that?
Yes, I mean, you see over here that the amplitude of the oscillations is very small in comparison, is smaller in comparison, for example, to the panel C or A, right? This is because in this case, H0 is very close to HF. Okay, so is the intensity of the quench is very low in this case. So you don't expect the spins to precess very much in this case, because H0 is very close to HF. So that's it. But if you, for example, compare the panel E over here of the Krylov complexity as a function of time with the corresponding one over here for the same H0 and HF of the magnetization as a function of time, you see that the scale in the vertical axis for all these panels are the same. The time goes from 0 to 150, and you see the same behavior. Okay, so that's it. So this is the explanation behind the necessary time to see these oscillations go to 0 and the graph stagnates in a specific value. Okay. All right. This is the main result that I want to show today. Okay. So given that behavior of the Krylov complexity as a function of time that I just showed, so if the complexity behaves exactly like the magnetization, then the long time average of this quantity should function as an order parameter for this dynamical filterization. And this is exactly what we get. Okay, so in the first row of this figure, I fixed the size of the system and I changed the pre-quench value of my control parameter. Okay. And in the second row of this figure, I did the opposite. So I fixed H0 and I increased the size of the system. Okay. And what I see is that you see these vertical dashed lines over here. Well, this is exactly the dynamical critical point, okay, calculated using that expression that I showed, H0 plus J over 2, okay? And you see that as I increase the size of the system, the non-analytical point of this curve tends to approach to the dynamical critical point of the usual order parameter, which is the magnetization, okay? And here in the insets, what I'm showing is the derivative of the main curve as a function of h0. And what I see is that the derivative of these curves assume higher and higher values as I increase the system size, okay? So what I can conclude looking at this result over here is that the time average at Krylov complexity works as an order parameter for the dynamic phase transition, okay? So, okay, when we got this result, we asked ourselves, okay, so the Krylov complexity behaves exactly like the magnetization. And we know that behind the dynamical phase transition, we have a breaking or a restoration of symmetry. So if the Krylov complexity is somehow sensitive to this breaking or restoration of symmetry, then somehow the Krylov basis should also be sensitive to this breaking or restoration of symmetry. And because of that, there should be a deeper relation between the energy basis and the Krylov base, okay? So then we started an investigation in order to understand what is the relation between these two quantities, between these two bases, the energy basis and the Krylov basis, okay? So the first quantity that we chose to perform this analysis is the so-called inverse participation ratio. The inverse participation ratio is the sum of the probabilities, which are given by this expression over here. And this is a dynamical inverse participation ratio because we chose to calculate this quantity using the system state in the time t, okay? So what we do is that we want to understand how many states of a certain basis is participating of the dynamics of the system. Okay, so what we do is that we project the system state psi of t in these bases, and then we calculate the sum of the probability. Okay, and we did this calculation using the Krylov basis. So we put here in this generic basis that I just I generically write as K. We used the Krylov basis and the pre-quench energy basis, which is the eigenvectors of the pre-quench Hamiltonian. Okay, and what we get was the following. So here I show the inverse participation ratio and the function as a function of time for the same values of H0 and HF. Again, the blue curves refer to quenches before the dynamical critical point and the red ones across the dynamical critical point, okay? And what we see is that when H0 is equal to 0, which corresponds to the panel A and B, so the inverse participation ratio in the Krylov basis, which corresponds to the dashed line here, and the inverse participation ratio in the pre-quench energy basis, which corresponds to the continuum line, they exactly coincide when H0 equals 0. But we don't see the same coincidence for different values of H0. So what is going on here? Why this H0 is so special when we compare it to the other values, okay? Another quantity, we also employed the Shannon entropy in order to understand the relation between the Krylov basis and the energy basis. So the Shannon entropy is calculated using this expression 15 over here, where the probabilities are this one for the Krylov basis and this one for the pre-quench energy basis, okay? And what we found was the following. Again, when H0 equals 0, the Shannon entropy in the Krylov basis, the dashed line, and the Shannon entropy in the pre-quench energy basis, the other line, they again coincide. So you see this coincidence in the panel A and B. But we don't see the same coincidence when H0 is different from 0. I mean, when H0 is greater than 0. Okay. So we asked ourselves, what is going on here? I mean, and we decided to take a closer look at the Hamiltonian. So please consider this special case when H0 equals 0. Okay. When H equals 0, the Hamiltonian has only the squared term. And this is a very simple Hamiltonian. We know all of its eigenvalues and eigenvectors. Okay, so its eigenvectors are the angular momentum state, the usual angular momentum states where mz goes from minus j to j. Okay. So then we turn on the magnetic field, then the frequency Hamiltonian now has the term proportional to H, which can be written using the ladder operators like this, okay? And then when we apply this post-quench operator in one of these usual angular momentum states, so what we get is this expression over here, equation 16, where the constant C0, C plus, and C minus is given by these expressions over here, okay? And if we compare this expression, the same expression, with the Lanczos recursive method that I showed previously, so what we conclude is that the Krylov basis, when H0 equals 0, must be exactly these usual angular momentum states, okay? The eigenvectors of SZ squared, unless a prefactor over here, which is -1 or +1, okay? So this result over here in equation 19, it explains why those curves, so it explains why the inverse participation ratio and the Shannon entropy coincide when H0 equals 0. Because those two bases, the pre-quench energy basis and the Krylov basis, are exactly the same in this case, okay? And because of this result, we get an exact expression for the Lanczos coefficients that I showed previously, which are no more than the normalizing constants of the Krylov states. And here in this graph, I show these Lanczos coefficients as a function of the number mz, okay? And here I have the dots, which were obtained using the Lanczos algorithm numerically. And here I also have a yellow line over each of these sequence of dots over here, which is, in this case, this yellow curve was calculated using this exact expression over here in the equation 20. And you see that they exactly coincide. So this is the exact expression for the Lanczos coefficients when H0 equals 0, okay? And because of this result over here in equation 19, then we can rewrite the Krylov complexity as a function of time in this way over here, okay? And now considering the expression of the total magnetization in the z direction, if you employ over here the completeness of these states, then you easily show that the Krylov complexity when H0 equals 0 is exactly the magnetization plus J, where this J here is n over 2, where n is the number of sites in the LMG model, okay? And of course, if you take the long time average in this equation, you find that the long time average of the Krylov complexity is equal to the long time average of the magnetization plus J. And of course, if you have a non-analytical point in this first term, the right-hand side of this equation, it will be exactly the same for the term in the left-hand side of the equation, okay? So this analytical result explains why the long time average Krylov complexity works as an order parameter for the dynamical phase transition, okay? All right, these were my results. So let me conclude this presentation. So I hope I convinced you guys that the Krylov subspace is a very powerful method to understand the dynamics in quantum systems, okay? And also that the Krylov complexity detects and characterizes these phenomena called dynamical phase transition, at least in the LNG model, okay? And there are a lot of open questions. For example, what is the Krylov basis when H0 is greater than 0? Okay. This is something that we didn't do yet, but so this is an open question. How does the long time average at Krylov complexity behaves near the dynamical critical point? That its derivative behaves like this, for example. What is this exponent gum over here? Does the long time average at Krylov complexity works as an order parameter in other models? This is an important question, of course, and we know that in the LMG model, this dynamical phase transition is directly related to the SQPT, the excited state quantum phase transition. So we could ask, are there deeper connections between the Krylov complexity and the SQPT? Probably, at least in the LMG, of course, we could make this link, but what about other models and so on? I mean, okay, so that's it. Thank you very much for your attention. And this is my contact. You guys can send me an email with questions or suggestions. And this is the website of my research group. Okay, so feel free to take a look there. You can find all the students and our publications and further information. Okay, so thank you very much.
Thank you very much, Pedro. It was very nice. Let me stop recording.